All right, hello my friends, welcome back. So I want to do a couple of optional videos to work through some extra examples of oligopoly problems and other types of continuous game theory setups. So as usual, right, with optional example videos, you're under no obligation to watch this. Feel free to stop this video right now, go outside, play with a hacky sack, whatever it is you want to do. But if you'd like to stick with me, we can work through this problem together. Okay, great. So the first optional problem I want to do is going back to our Cournot oligopoly setup, where we have two automakers, right, Ford and GM, each of whom is producing trucks. But this time, instead of having the same marginal cost for Ford and for GM, we're going to think through how this problem is going to look when the two companies have different marginal costs. So in this case, right, where we've got a cost function for Ford, where the cost of producing Q trucks is 40,000 Q. So we're going to have a marginal cost for Ford that's just 40,000. And where the cost for GM is 20,000 Q, right? So their marginal cost is going to be 20,000. Great. And we've got an overall demand for trucks, right, that's given by this, 100,000 minus 2 big Q, where big Q is just little qf plus little qgm. Make sense? Beautiful. Okay, so as you might remember, the way that we want to approach this problem is that first we're going to try to find the best response functions for each of the two companies, right? So our first step, our first step is going to be best response from each company. And what we mean by our best response, right, is let's imagine that Ford knew how many trucks GM was going to make. Then we ask, what's the optimal number of trucks for Ford to make in response to whatever GM is producing, right? So this is going to be, for Ford, their best response is going to be QF as a function of QGM. And for GM, their best response is going to be QGM as a function of QF. Wonderful. Okay. So let's start with Ford. Right? So in this case, what we know is that they have a demand curve here that's going to be an inverse demand, which is going to be P of Q F QGM equal to, I'm going to rewrite this so that it's clear that it's a function of QF, right, taking QGM as a given. This is going to be 100,000 minus 2 times QGM minus 2QF. Good? Okay. Right, and then our marginal cost is going to be 40,000. So how are we going to choose our optimal number of trucks? Well, what we're going to do, right, is we're going to say, essentially, what we have is a downward sloping demand curve, right? We have a demand for trucks, like this. We have a marginal cost, like this, right? What we want to do is we want to produce where marginal cost equals marginal revenue. This makes sense? Once we take GM's production as a given, this is just a standard demand curve, or a linear demand curve, where the price depends on the number of trucks Ford produces. So we just need to find our marginal revenue. Right, this is going to be P of Q right, plus the P to Q times Q. Great. So this is going to be 100,000 minus 2 times QGM, right, minus 2 QF, right, this is PQ, dP dQ is the derivative of this with respect to QF. I'll make this clear. dP dQf times QF, right? Since this is Ford, choosing Ford's production. So this is just going to be -2 times QF. Beautiful. So we're going to end up with marginal revenue that is 100,000 minus 2 QGM minus 4 QF. Beautiful. Right? This makes sense? Wonderful. What do we do once we find our marginal revenue? Well, we're just going to set this equal to marginal cost, right? We're going to produce, I'll erase my little drawing. We'll produce where marginal revenue equals marginal cost. So we'll produce where 100,000 minus 2 QGM minus 4 QF is going to equal Ford's marginal cost, which is 40,000. Awesome. Okay, so now that we've gotten here, I want to take a moment to pause and think about what our goal is, right? Remember what our goal is. Because now we've got an equation here with two variables, right? QGM and QF. But remember that because we're looking for our best response function, right, where we want to know, given what GM produces, what's Ford's optimal output in response, we want to treat QGM just like a number, right? We want to treat this like a constant. So we really only have one variable in this equation. The only variable we need to worry about here is QF. So our goal should be to isolate QF to get QF as a function of QGM. Good? So let's do it. So I can subtract 40,000 from both sides, add 4 QF to both sides, and get 60,000 minus 2 QGM equals 4 QF. Right? Divide both sides by 4, and I'll get QF as a function of QGM is going to be 60,000 over 4 is 15,000 minus 1/2 QGM. Right? 1/2 because 2 over 4 is 1/2. Beautiful. So this is our best response if we're Ford to what GM produces. If we spend a minute to think about what this is telling us, it's telling us that if GM was out of the market completely, Ford would essentially be a monopolist. Right? If Ford's a monopolist, their optimal output would be 15,000. And this would make sense, right? Because their marginal revenue, if they were a monopolist, would just be 100,000 minus 4 QF, right? The difference between the maximum price and their marginal cost would be 60,000, right? 60,000 divided by 4, 15,000. Beautiful. It's also telling us that each time GM produces more output, Ford responds by producing a little bit less output. And this makes sense because essentially as GM produces more, they're soaking up demand, lowering the price at which Ford can produce their stuff. We should also notice that we have a 1/2 here, right? This means that if GM decides to produce more, Ford's not going to pull back production so much that production doesn't increase, right? GM's decision to produce more will still result in more trucks on the market. Okay, great. So we've got our first best response function, 15,000 minus 1/2 QGM. Great. So now let's do exactly the same thing to find GM's best response to Ford. Okay. So they're going to have this same demand function, right? Now I'm going to rewrite it to have GM last, right, to show that Ford is being taken as a given. So it'll be 100,000 minus 2 QF minus 2 QGM. Wonderful. Our marginal revenue is going to be, right, P of Q minus dP dQF, I'm sorry, dP dQGM, right, we're doing GM now, times QGM, yeah? So this is going to be 100,000 minus 2QF minus 2QGM. This is all P of Q, right? It's all P of Q. Plus dP to Q, which is going to be negative 2 times QGM, right? Wonderful. Wonderful. Okay. So from here, right, we combine like terms. We say that our marginal revenue of F, marginal revenue of G, I'm so sorry. I don't know where my head's at today. Right, our marginal revenue for GM is going to be 100,000 minus 2QF minus 4 QGM. Wonderful. And just like before, right, just like when we were thinking about Ford, we want to produce where marginal cost equals marginal revenue, because if we take the amount of number of trucks that Ford produces as a given, right, the remaining demand is only going to be met by GM. GM is going to think about this problem just like a monopolist would. Okay, great. So we'll say marginal revenue equals marginal cost, right, 100,000 minus 2QF minus 4 QGM is going to equal the marginal cost for GM, which is 20,000. Right, if I solve this for in terms of GM, right, because again, to pause for a second, when we were over here, right, we were treating QGM as a constant, trying to solve for QF. Now we're doing exactly the opposite. We're treating QF as a constant, trying to solve for QGM. Right, so we can say 80,000 minus 2QF has to equal 4 QGM. So QGM as a function of QF has to equal 80,000 over 4, right, which is 20,000, minus 1/2 QGF, or 1/2 QF. Beautiful. And this is GM's best response to Ford. So we should note this looks very similar to Ford's best response to GM. Excuse me. The only difference is that because GM has lower marginal cost than Ford, if they were a monopolist, right, if Ford didn't produce anything, they would produce a larger number of trucks than Ford would if GM wasn't producing anything. Wonderful. Okay. Okay, so what do we do now that we've found our two best response functions? Well, what we want is we want our Nash equilibrium, right? And what a Nash equilibrium is it's a set of choices, QF and QGM, where QF is a best response to QGM, QGM is a best response to QF. In other words, if both companies know what the other company is going to do, neither company has any reason to change their behavior, right? This is the sense in which we're in an equilibrium. No individual has an incentive to deviate. So our second response, find Nash equilibrium. Right, this is going to be where QGM, best response to QF, and QF, best response to QGM. Great. So how do we do this mathematically? Well, if QF is a best response to QGM, QF has to equal 15,000 minus 1/2 QGM. This make sense? If QGM is a best response to QF, QGM has to equal 20,000 times 1/2 QF. So what we can do is we can say, right, QGM has to equal 20,000 minus 1/2 of QF, which is in turn equal to 15,000 minus 1/2 QGM. This makes sense? So this is essentially asserting both of the two things that have to be true at the same time, right? Saying QGM has to be a best response to QF, QF has to be a best response to QGM. By making these two assertions, we end up with an equation just in terms of QGM. Wonderful. Okay, so let's distribute first. I'll say QGM is going to be 20,000 minus 1/2 of 15,000, so that's 7,500, minus 1/2 times 1/2 QGM, that's plus 1/4 QGM. Pull everything over to one side, so I can say 3/4 QGM is going to be 20,000 minus 7,500, which is going to be 3/4, which is going to be 12,500. So then QGM is going to be 4/3 times 12,500. And this is equal to 16,667. Okay, great. So what we're saying is, when GM is producing their optimal amount in response to Ford producing their optimal amount, GM's going to end up producing 16,667 trucks. How about Ford? Well, Ford has to produce their best response to 16,667, right? So we can say QF in response to 16,667 right, has to equal 15,000 minus 1/2 times 16,667. Make sense? Great. So this is going to be 15,000 minus, well, 1/2 of 16 is 8. 1/2 of 666 would be 333. Good? Good. So this is going to be, well, 15 minus 9, right? So 6,667 trucks from Ford. Great. So at the end of the day, right, we figured out our optimal output from each of these two companies, right? GM is going to produce more trucks than Ford. This makes sense because GM is a lower cost producer than Ford, but Ford is still going to produce some trucks despite the fact that their marginal costs are double the marginal costs of GM, right? So we have a situation here where Ford is producing almost 7,000 trucks at $40,000 a truck. GM could have produced those trucks, each of those trucks at $20,000 a truck. So essentially, as a society, we're wasting $20,000 per truck by having Ford produce those trucks. The advantage from society's perspective is that our total output of trucks, big Q, is going to be 1,667 plus 6,667, which is going to be 23,333. So we're going to get about 3,000 more trucks, 3,333 more trucks, by having GM in the market, or by having Ford in the market, putting pressure on GM, than we would have if GM had been a monopoly supplier, right? So the cost to society is that we have these, basically 3,333 trucks being produced at high cost that would have been produced at low cost. The benefit to society is we get another 3,333 trucks that wouldn't have been produced at all. Right, the other benefit for consumers is that our price is going to be lower. Right, our price is going to be 100,000 minus 2 times 23,333. So that's going to be 46,666. So our trucks are going to cost $53,333. Make sense? Whereas if GM was producing by themselves, they would have produced 20,000. The cost of a truck would have been $60,000. Okay, fantastic. Okay, thank you so much for sticking with me. I hope this was helpful. I'm looking forward to talking to you about examples like this when we meet in class. All right, excellent. Thank you very much.